In this lecture, we now want to introduce the concept of a random variable. Intuitively, the random variable is any kind of property that you can measure on the samples that you're getting. For example, you have the population of the world and you want to measure the height of everybody. So your probability measure is defined on the space of all persons on the world, and it assigns a probability of sampling a particular person. But the property we're actually interested in is how tall is this particular person, or what is the income of this person, or in machine learning you might even be interested in other kind of properties. And sort of evaluating properties of elementary events that in our elementary objects that are in our probability space, this is what is typically modeled in terms of random variables. Another example you could consider is you throw a die twice, and you want to consider the sum of the results of the die. Then your probability space would consist of the elementary events that you could get, but what we're actually interested in is the sum. And this is now the concept that I want to formally introduce, and all of probability theory is based on random variables. So this is sort of one of the most important, next to a probability measure, I think this is the most important definition that's out there. So let me define it. We consider a probability space. So let omega AP be a probability space. Maybe I should write B as well. Be a probability space. And now, so this is the space of the objects that we can sample. But now we're interested in taking some kind of measurement on these samples, and these are going to end yet in a different space. So we need a second space. So let, how did I denote it? Omega tilde A tilde be another measurable space. This is going to be the target space. And now we consider a mapping that is often called X. So the sort of the typical letter for a random variable is X, and random variables are also by default being denoted by capital letters. So X is now a mapping that goes from omega to omega tilde. So you take one of your sampled objects and you sort of evaluate what is the property that you're interested in. So omega might be persons, and omega tilde is how tall is this person. So a mapping is called a random variable if, now there's an important property that we now need. If X is measurable, so X is formally, from a mathematical point of view, X is a function that goes from omega to omega tilde. And when is a function measurable? It's measurable if for all sets in the target space that are in the sigma algebra of the target space, the pre-image is in the sigma algebra of the original space. Let me first write it down and then I give you the intuition. That is, for all sets A tilde that live in the sigma algebra A tilde in the target space, we have that the pre-image of A tilde under this mapping. So let me write down formally what this is. So these are the omegas in the original space omega such that X of omega ends up in A tilde. This set needs to be in element of A. This is now complex. Let me try to explain many things here. First of all, what is this pre-image here? This x to the power of -1, observe it doesn't mean that there's an inverse map or anything like that. It's just the standard notation for the pre-image. So we look at all points omega in the space such that x maps this in the set A tilde. So maybe I simply make a drawing as well. So here we have our space omega. And here we have the space omega tilde, that's the target space. We have this mapping X that goes between the two spaces. And now we have some set A tilde that lives, so it's in the target space. and it is part of the sigma algebra of the target space. So remember, the sigma algebra tells you which are the sets to which we want to assign probabilities. And now the property is that if we take that set and consider now, there might be different points that are being mapped to this. So there might be another set here, A, and this set is being mapped to A tilde. And now what we want to say is, we want to say that this map A now also needs to be measurable in terms of the probability measure that we consider. And this is supposed to hold for all the sets A tilde that we can construct. Now, what is the intuition why we need this definition of measurability? So assume you want to say something like, let me make an example here. So this is the people in the world, and this is the height of the people. And now what you want to say, I want to, for example, say, what is the probability that someone is at least 1.70 meters? So we could here have the set A tilde, which is at least 1.70 meters, 170 centimeters. And now this is something that lives on the space omega tilde. So on this space we currently don't have a probability even yet. We just assume that A tilde is one of these sets where we want to assign the probability to. And now to assign a probability to, what do I need to do? I need to go to the original space and figure out among all the population of the world, if I would sample all these and these people, they would be at least 1.70 meters, and then I need to count them and figure out what is the probability of sampling these people. So here you would have the persons that are at least 170 centimeter tall. And for this, to this set here, this is our set A, and this here is the set A tilde. Oh, that's maybe not a good notation, let me do it differently. So to this set A we can assign a probability because, and we want to be able, that's the crucial thing here, we want to be able to assign a probability to this set A, because then we can say the probability of A is, I don't know, 0.1, and then we can also say, once we know this, we could also then say the probability that of the set A tilde, we can assign the same value to that. But this can only work if, when we start with a set A tilde in the target space and we go back to the people that satisfy the set, this is a measurable set, so this is in our sigma algebra. And so this is the definition we make here. Let me say it once more. So we have this original space. This is the space we're actually interested in, the target space. We consider this mapping, and the mapping is measurable. This means whichever set A tilde I choose in my target space, if I consider the objects in my input space that satisfy this property, they need to be measurable in the sense that they are in the sigma algebra of the input space, so I can assign a probability to that. And whenever we have a mapping X that satisfies that, it is called a random variable. Wow, that sounds like a complicated construction to measure the height of people. Let us maybe again look at a couple of examples to make it a bit more clear. Example. And I want to show the examples that I've already mentioned in the introduction to this lecture. We look at the sum of two dice. Sum of two dice. So our probability space, this consists of what are the things that we can actually sample. So typically if we have a dice and we throw it twice, or we have two dice, say, what are the events? Our events would look like this. We have two numbers, the first result and the second result. And this have to be numbers between 1 and 6. So I and j are in 1 to 6. So this is the space of the elementary events that we have. Then as our sigma algebra, we use the power set again. So all possible combinations. And as the probability we need to define the probability measure, and we do this by defining it on each of these elementary events and simply assigning the probability 1 over 36, so it's the uniform probability essentially. So everybody has, like all combinations have the same chance. And now, so this is for now, we don't have any random variable yet. So this probability space typically models these kind of elementary events that we would have. And now we want to define a random variable x that is sort of the sum, just the sum of the two values. So this is the intuition that we want to have because we might be interested in that. And now how do we do that formally? So formally, x is now a mapping that goes from omega to the space 2 to 12. So these are all the possible values the sum could take. And we simply map the pair ij to the sum I plus j. So this is the mapping. A random variable is a mapping. We have now defined it. And now we formally need to check that this mapping is measurable. And in this case, this is easy because everything is discrete and, sorry, I didn't define what is the space omega tilde. Maybe I write this down as well. So I write down omega tilde, that's the space 2 to 12. And I didn't, this is why it occurred to me, I didn't define the sigma algebra. The sigma algebra is again the power set, the discrete sigma algebra. And now to say to observe whether this is measurable, I need to check for all elements in this power set whether the original set that would correspond to that is a member of the sigma algebra. And it has to be because the original sigma algebra is the power set, so every set is in the sigma algebra, so it is obviously measurable. Okay, so this is the sum of two dice. Now I want to introduce two more notions, namely what is now the, I might have used this word already, but what is now called the distribution of x. Sometimes the words distribution and probability measures are sort of used interchangeably, but formally a distribution is something that is associated to a random variable. Let me define it. A random variable x from omega to omega tilde induces a measure on the target space. Namely, this is what I already described intuitively above. If we go back, here we had this example of the height of a person, and I said I want to define the probability that someone is at least 1.70 meters, and I said in order to define that I need to check out what are all the persons that have 1.70 meters height and what is their probability measure, the probability measure of that set of persons. And this is exactly what is going on now. So we define, so for A tilde in A tilde, so A tilde, I don't repeat the notation, is the sigma algebra on the target space. We define, and this is now often denoted as P sub x of A tilde, so the probability measure of A tilde under this random variable x. And this is simply defined as the probability of the pre-image of A tilde. So we take A tilde, being at least 1.70 meters, we go back to the original space, check who are the people who are at least 1.70 meters and compute their probability. Okay, and this measure is called the distribution. So this is a probability measure. So this maybe the first thing is, this is a probability measure on now this target space, omega tilde A tilde, and it is called the distribution of x. and the letter that is often used is px. Okay, and observe, I mean, there is something one would formally need to prove here, that this is indeed a probability measure. I mean, first of all, it is a function that goes from a tilde to the real numbers. That's fine. And observe that we need the measurability here to be able to construct this probability measure in the first place. And then you need to prove that it really has all the properties we need for a measure, in particular countable additivity. But all this is really easy, because whatever you want to prove on the target space can be proved by going back to the original space, and there we have it, because we started with a probability measure on the original space. I want to make one more definition, because we might need that later on. So observe here, here we looked at the sigma algebra on the target space. And then we said we want the random variable to be measurable. That is, we need to achieve that for all the for all the sets on this target space in the sigma algebra, the pre-images here, these guys, are measurable in the original sigma algebra. Now sometimes it is a bit unclear which sigma algebra I should choose on my target space, because I mean like the space I know essentially is this original space omega, like the set of all people in the world and the probability of sampling each of them. So here sort of, this is the space I know. Here I also know what kind of sigma algebra I want to construct. Now on the target space I might even have different choices of constructing the sigma algebra, because maybe I want to have more events that are measurable or less events. And now the question is, what is the minimal number of events that you would need to make this a sigma algebra? And that was wrong. Because what I was going to introduce is the sigma algebra on the original space. Put a marker. Now there's one more concept I want to introduce, which is the sigma algebra induced by a random variable. Let me maybe write it down first and then I explain it. So it's a definition. So consider a random variable x that goes from omega a p to omega tilde a tilde. And now we define sort of what is the smallest sigma algebra on the original space that we can afford to still make that thing a random variable. So observe, let me maybe go back to the definition. So a random variable is something that is measurable. So we start with a set in the target space and then want that the pre-image of that set is in the original sigma algebra. Now, of course, one can play with how one constructs a sigma algebra. So it could be that you have different choices for the sigma algebra. And if you say, I really want to measure what is the height of people, then you can ask yourself, what is the smallest sigma algebra that I actually need to make that a random variable? So if you already know in your mind what is the mapping X that you want to consider, what is the target space, so this is typically what you know, you want to measure the height of people, and it is also sort of maybe in your mind it's clear what the sigma algebra A tilde is, so it's sort of all reasonable events that you might want to express about the height of people. And then you can ask yourself now, what is the sigma algebra A that I need on omega such that the mapping is then in the end measurable? And this is what we now define. This is exactly what we're going to do right now. So we have now a random variable, and then we define a new sigma algebra. So then the family, then the family, so it is called sigma of x. So the sigma algebra induced by the random variable x simply consists of all the pre-images of the sets A tilde, where A tilde are the sets in capital A tilde. Right? So we look at, so this is sort of the minimal set that we need to have to make this set measurable. There could be, and it wouldn't help for the fact of whether X is a random variable or not. It doesn't really help to add more sets to the sigma algebra in the original space. It doesn't help, it doesn't hurt, it doesn't make any difference in terms of this random variable. So then the family blah is a sigma algebra on the original space, and it is called the sigma algebra induced by X. And if you want, you can also characterize it as the smallest sigma algebra that you can have, such that X is really a random variable, such that X is measurable. And maybe I write this in red as a remark. It is the smallest sigma algebra on omega that makes X measurable. Okay, so what do we have? We have the sigma algebra induced by X. And now we have seen what are all the basic notions associated to a random variable. So we have seen what is the random variable. It is simply this measurable set. We have seen what is the distribution of the random variable, namely the probability measure that we end up on the target space. So that's the thing we're actually interested in. And sometimes for mathematical convenience, we need to look at the sigma algebra induced by X on the original space, which helps us maybe to construct these whole things. And typically this is something you might want to need in a proof or so. It's not something that, like the sigma algebra, is not something that you would need in your daily machine learning expertise. Okay, and now in the next lectures we're going to see what are all the interesting statements we can make about random variables. That is essentially the essence of probability theory.